Hi, so welcome to this next session. And in this session, we are going to be exploring how we estimate intra-cluster correlations at the design stage of a trial so that this can help us determine what is the required sample size in a future study. So what we're going to do here is to illustrate how we might estimate one of these ICCs from routinely collected or maybe some trial data. And we're going to do this for both continuous outcomes and binary outcomes. And then we're going to go on to look at some extensions for how we might estimate these within cluster correlations if we were trying to design a multiple period cluster design. And specifically, we are going to look at the estimation of the within period intra-cluster correlation and the cluster autocorrelation. We'll also talk about a few caveats that we have to be aware of, which influence the stability of these estimates. So thinking specifically about how many clusters are required to get a good estimate of these parameters and what the required cluster size might be, again, to get a stable estimate of these parameters. So just as a reminder, why do we need to estimate these correlations? Well, we need to estimate these correlations both at the reporting stage of a full trial, but also they're needed at the design stage. So at the design stage, we need these estimates so that we can properly inform and calculate our sample size requirements. At the reporting stage, we need to report these estimates because this is part of the consort reporting guidelines. And ultimately, the idea behind reporting them is to help others inform and plan future trials. So what data is required if we want to estimate these within cluster correlations? Well, we need information on the outcome of interest, the cluster, period of the observation for multiple period designs, and also the treatment arm. And this is needed only when we're estimating correlations in completed studies at the reporting stage. And if we're using routinely collected information, this variable here would be redundant treatment arm. So when we're estimating to inform a sample size calculation, there are a few things that should be similar to the planned study. So clusters need to be similar, the data collection method needs to be similar, the outcome needs to be similar, and in longitudinal studies, the time period also needs to be the same. And that's because these estimates are estimates of within cluster correlations. They inform us how similar observations are within a particular cluster. Now, if we change the cluster, we change the outcome, we change the method of data collection, or we change the time period, then this can distort those correlations, and they no longer represent correlations that we might occur in our own study. So similarity here is key. So part one then, what we're going to do first of all is think about how we might estimate these ICCs in the simple setting to inform a parallel arm cluster randomized trial design. Okay, so there are a couple of simple steps. The first step is we fit a mixed model without any covariates if we're using routinely collected data, or we might put the treatment covariate in if we're at the analysis stage. So we fix this model to get our variance components. And so then from these variance components, we can estimate our intra-cluster correlation using the notation rho. And this is the ratio of the within to the within plus between variance components. So we're going to illustrate this process in the parallel arm cluster randomized trial where the outcome is a VAS score. So we've seen this example before. Remember, the data comes from a parallel trial. We're going to combine all of our treatment arms here just for simplicity. It's got 39 clusters. The variable in the data set that denotes the cluster is ID class. The outcome is the VAS score. It's measured on the scale 0 to 100. In our data set, this is coded by the variable Y. And we might or we might not put in the treatment as a covariate. It's not shown and it has minimal impact. So in data 17 for a continuous outcome, this is how we might implement that procedure. So the first step is to fit a mixed model. So the code in Stata is mixed. We tell Stata what our outcome is, what our cluster variable is, and this no log here just says that we're not interested in all the intermediate log of the output. So it fits a mixed model for us. There's no treatment in this model, so the fixed effects are not terribly informative. But what we're interested in here is these random effects parameters, the within cluster variance and the between cluster variance. And Stata provides us estimates or point estimates of each of these variance components, a standard error, and a confidence interval. And then to estimate the ICC, we can use this command called estat-ICC in Stata. And this then provides us with a point estimate of the ICC and a 95% confidence interval. So that's the implementation in Stata 17 for a continuous outcome. How do we estimate the ICC for a binary outcome? It's actually unintuitive. So the ICC for sample size calculations for binary outcomes need to be on the proportion scale. So estimating an ICC from a logistic regression would provide an ICC on the logistic scale, and that's not the right scale. So the solution is to fit a mixed model to the binary outcome. And then from those variance components, we can estimate the ICC on the proportion scale. So fitting a mixed model to a binary outcome is the unintuitive part. So again, let's illustrate this in the example. So remember, it's the same parallel cluster trial, but there's a binary outcome as well. And the binary outcome is whether or not the participant used pain medication. So again, we're going to combine the treatment arms. We're assuming that we've got 39 clusters, and now we're working with the outcome, which is denoted by Y bin in our data set. It's a binary outcome, whether or not pain medication was used. And again, we haven't added in treatment here as a covariate. We could do, it would be appropriate if we were reporting this IC at the end of the trial. In this particular setting, it's got minimal impact. So implementation in Stata 17 for a binary outcome. Step 1 is to fit a mixed model. So we fit a mixed model to our binary outcome, we tell Stata what our cluster ID is, and it provides us again with the variance components. Now the unintuitive part is fitting a mixed model, not a logit model, to a binary outcome. And then again, step 2 is to estimate the ICC. We could do this by taking the ratio of the two different variance components, so the within divided by the sum of the within plus the between. And if you want to work that out by hand, you'll see that that indeed does come to this value here that Stata provides us with. But if we did that, we wouldn't necessarily know how to obtain confidence intervals for that point estimate. And so using the estat-ICC command in Stata just allows us to get these confidence intervals with minimal hard work. So in part 2 then, we're going to go on to think about how we might estimate these within cluster correlations, not to inform a parallel design, but this time to inform a multiple period cluster randomized design. So remember, when we're designing a multiple period cluster randomized design, there are different assumed correlation structures that we might adopt. So here we're just going to consider the setting where we are going to use a correlation structure which can be parameterized by the within period ICC and a cluster autocorrelation. So this comes from a model with a random cluster effect and a random cluster by period effect. We're only going to consider continuous outcomes for the multiple period design, although this issue of scale, logit versus proportions, is likely to be relevant for binary outcomes here as it was in the setting of parallel cluster designs. So that's to say, if you are interested in estimating within period ICCs and cluster autocorrelations for binary outcomes, it's probably appropriate to estimate those on the proportion scale and not the logistic scale. So again, there's a couple of simple steps. So the first step is to fit a mixed model. This time we have to add in a random cluster effect and a random cluster by period effect and a categorical or fixed period effect. And again, put treatment covariate in if this is at the analysis stage of an RCT. And then from that fitted model, we obtain some variance components. And from those variance components, we can estimate the within period ICC and the between period ICC. And then remembering that the cluster autocorrelation is the ratio of these two correlations, we can take the ratio of them to obtain a point estimate for the cluster autocorrelation. And then we have to use some method to obtain 95% confidence intervals for the cluster autocorrelation, because there isn't a inbuilt command in Stata that will do that for us. So I'll provide you with a bit of code that will allow you to do that. So let's have a look at our example. So this time the example is from a different setting. The outcome is BMI. It's from routinely collected data from UK general practices. The general practice we're thinking is the cluster. So there are 425 clusters in this data set. Each person contributes one measurement to this data, so it's cross-sectional. But the measurements are taken over a number of years, and we're going to set one period to be 1 year. And in total, there are going to be 4 periods or 4 years in the data set. So the histogram on the left-hand side shows us the distribution of the individual BMIs across the data set. And then on the right-hand side, the box whisker plot just simply plots the cluster level median of the BMIs across the different clusters. And this just gives us some idea of how those cluster level medians in this case vary across the different clusters. So to implement this in Stata, first parameter that we're going to try to estimate is the within period ICC. So again, there's 2 steps. The first step on the left-hand side is to fit the mixed model. So this time we're fitting a mixed model. Our continuous outcome, we're putting in a fixed effect for time periods, a random effect for cluster, and a random cluster by period effect. And then Stata just tells us how many clusters and how many periods we're working with. So we've got 428 clusters. These are our 425 GP practices, and then in total there are around 1,700 cluster periods, and this is roughly equal to the 425 clusters multiplied by 4 because we've got 4 periods in this data set. Stata provides us a fixed effects components, so this time we've put in a categorical effect for periods, so we've got 4 fixed effects for the 4 different periods. And then of more importance to us is the variance components. So Stata gives out 3 different variance components. One is a within period variance, one is a between period, and the other is a within cluster period. So these are our 3 different components of variance. Now if we run the function estat-ICC, then Stata will give us some estimates of correlations and 95% confidence intervals. And the ones it actually provides us with, although the language that Stata uses is not terribly informative, these are the between period ICC and the within period ICC. And so one of these is important for our sample size calculations, the within period ICC. So we've got an estimate for the point estimate and a confidence intervals. So that's estimation of the within period ICC. But notice that this output gives us the between period ICC as well, but it doesn't give us a cluster autocorrelation. And it's the cluster autocorrelation that is often needed for sample size calculations. So we could estimate the cluster autocorrelation by hand, remembering that the cluster autocorrelation is the ratio of these 2 within period correlations, within period to the between period. We've got point estimates of these on the previous slide, so it turns out that our point estimate of the cluster autocorrelation is 0.86. That doesn't provide us with any confidence intervals. So if we wanted confidence intervals for that, we could obtain confidence intervals by bootstrap. And there's a little bit of code on the next slide that provides some Stata code for how we could implement that. And it turns out that this bootstrap method for confidence intervals provides us with this confidence interval here, which we might think of being a upper and lower bound in our sample size estimation. And so here's the Stata code if you wanted to replicate that. So bootstrap confidence intervals for those correlation parameters. Couple of points to note is that we could use this code to estimate the confidence intervals for all the parameters, not just the cluster autocorrelation. And the bootstrap here is by cluster and not by individual. So other potential issues that might be worthy of some consideration here. So what estimation procedure is the best estimation for these correlation parameters? So we spent some time thinking about small sample corrections. Now these small sample corrections affect and influence the standard errors of the fixed effects, but they do not affect the variance components. So those small sample corrections, if you like, are irrelevant. But nonetheless, if we have small samples, then these between cluster variances are typically biased downwards. So that's one thing to note. The other thing to note is that this function ESTAT-ICC that we've used here, this data function, uses maximum likelihood estimations and confidence intervals using the delta method. Now, other approaches, rather than the delta method, might be optimal, particularly in small samples with binary outcomes. So the ESTAT-ICC is just one method for estimating these confidence intervals, and there are others available that might be more optimal in some things. Other thing to think about is how big does my data set need to be so I can get reliable estimates of the ICC? So to get reliable estimates of these within cluster correlations, we need to have either a large number of clusters or a large cluster size. And exactly how large depends on the underlying ICC. So for large ICCs, it turns out that we need smaller samples, but for smaller ICCs, we need larger samples to get stable estimates of them. And if we use a data set that's too small, the estimates of the ICCs can be downwardly biased. We should always include some measure of uncertainty whenever we're reporting ICCs. So here are a few of the methods references that we considered in this session. And up next, we are going to go on to think about how we might do the same, but this time rather than use Stata, implement this methodology in SAS.